Today what I'm going to do is I'm going to talk about deep foundations for transportation facilities, and I'm going to look at it from the standpoint of a historic view as to what TxDOT's done. What I'm going to do is I'm going to look at the foundations, the use, a little bit of design history, touch upon just major events that have occurred, and then finish with some things that are being done currently. In the past, TxDOT's used a variety of foundations, spread footings, driven piling, and drill shafts. Spread footings were predominantly used early on. They were used in basically competent soil and rock. They were used up till the 70s, but I would say from about the mid-50s on, their use became less and less, and that was with the advent of drill shafts. Piling have been used all throughout, as you can see, in a variety of ways. Typically used in softer soils because the piles that we've used are typically displacement piles. Drill shafts began, surprisingly, in the late 1940s, the first in the U.S., and then have progressed ever since. They're used in a wide variety of conditions, and are used today as the dominant choice for foundations. TxDOT's generally considered to be the largest user of drill shafts, and our drill shafts are the least expensive, at least in the United States. So in the past, spread footings were used, and typically, as you see on the left, in river environments and with rock involved. The ones that were used in river environments without rock typically didn't survive. On the right-hand side, you see a typical spread footing foundation, and in the past, the use of web walls. So in terms of, now I'm going to talk exclusively about our deep foundations because that was a shallow foundation, and I'm going to begin with piling and then finish this segment with drill shafts. Piling has a long storied history with TxDOT. It's been here since the beginning. Began with timber piling, then went to pre-stressed concrete piling, steel H piling. In the mid-60s, metal shell piling was introduced, and then in 1993, metal shell piling was removed. And the reason for that was the advent of drill shafts. One point I'd like to point out here is if you look in 1925, TxDOT was way ahead of its time in terms of scour. Why? In the 1925 spec book, it said to use piling, if possible, to try to prevent against scour or erosion, all right? And when we think about the history of things, in 1987, some 62 years later, the Schoharie Creek Bridge came down on a spread footing without any foundations under it. In the past, the installation typically involved lighter weight rigs than we see now. On the far left, you see a rig about the year 1942 with the air steam hammer mounted on the back of a truck. As we progress, they've got a little bit bigger, piling got a little bit longer, and then the one in the middle in the mid-50s is an air steam hammer again, and then we progress to the 60s where diesel hammers first came into play. The use of piling, or today, we changed to many different hammer types. On the upper left is a modern version of a diesel hammer. The upper right shows vibratory hammer, which is used for steel piling and in particular sheet piling. And now we have a hydraulic hammer, which is used throughout, mostly on our coastal ranges. But if you look on the right-hand side, the lower right-hand photograph, it can also be submerged in water, which is a great advantage because cofferdams no longer have to be dewatered at this point. They can be dewatered later. Our piling types that we've used, everything from timber piling to steel H piling to steel pipe piling or metal shell piling, but throughout our storied past, concrete piling has really been the mainstay. You see in the top right, concrete piling being used for a footing. In the center part, concrete piles that are used as trestle piles on a bridge crossing a stream. And then the lower right, of course, battered piles often used at abutments. Drill shafts have a little bit different history because piling were used nationwide, and so their introduction was not surprising. But drill shafts, Texas really started and began a lot of the surge to use drill shafts. In the 1930s, several companies, and in particular around 1932, several companies in Texas private companies began using drill shafts. And you see the rig up there, it looks a lot different than what we see today. They were introduced in the late 1940s. By 1948, they actually were introduced to use on bridges here in Texas, included in the specs in 1950. One of the things was, a very common feature we'll see in a minute, was the use of belt-shaped footings on drill shafts. And therefore, with the belt-shaped footings, they would lower an individual down in the hole to make sure that the hole is cleaned. And in this day and age, the diameters of the holes were basically anywhere between 18 to 36. I don't know about you, but I wouldn't want to be the gentleman or individual being lowered down in the hole. That practice actually continued and was actually suspended somewhere early 80s due to confined space. In the 60s, slurry was introduced, and then in the 1970s, we'll see later on, belt shapes really started to diminish and have since gone away. Also, beginning in 1968, TxDOT embarked on doing research, and the research began at the University of Texas and then proceeded to University of Houston. At the University of Texas, Dr. Reese did a lot of the work. He did a lot of the work on construction, axial loading, and lateral loading of drill shafts. And then when he retired, Dr. O'Neill finished that work off. That was very interesting and very good work. It changed our direction on the use of drill shafts, we'll see in a minute. But also, it helped provide the standard for the rest of the states and the rest of the U.S. to be able to use drill shafts. And all that information was included in the FHWA drill shaft manual. Now, what did drill shafts or construction equipment look like back in the 50s? Well, anyone who's been around drill shafts recently would look at these rigs and think that these are fairly small, and they are. They were very limited on the depths that they could drill, the diameters that they could drill. On the left, you see a crane-mounted rig, which basically was limited to, again, 12 to 36-inch shafts, and was very limited in rock. On the right-hand one is a truck-mounted rig, much smaller, basically drilling just through the hard upper surface layers. As I stated before, bell shapes were very common back then. You see on the left the bell-shaped section at the bottom, and basically they were designed as if they were spread footings, and so based on bearing at the bottom. On the upper right, or the center and upper right, you see two different apparatuses for creating bells. The one in the middle is what's called a wing-shaped or wing section. Basically, the center part actually flares out. A screw goes down the center of it and pushes the two wings out to create the actual bell. And on the right is what's called a flap or a flare. Basically, there's two flaps on it. Those are extended due to a twist again, and they create the bell. This is, incidentally, again, where the individual would be lowered down to check the bottom of the hole, because visually we couldn't see the actual bottom. Today, our drill rigs look a whole lot different, much larger, have much more or much greater torque on them. And so what we see is on the left, a more modernized rig, and on the right, a much larger and more powerful rig. Both are capable of drilling up to about, on the left, 8 foot, and on the right, a 10-foot diameter, and sometimes 12 foot, depending upon soil conditions. So these are much larger and much bigger, and they also can drill much faster. So in addition to our history on the usage, right, we've also undergone changes in design for our foundations. And I'm going to look at the history on our Texas cone penetrometer and then briefly just touch upon our correlation charts. In terms of history, this was outlined in a recent research project, but our history began in the 30s, and essentially that's when development was done. This is exactly the same time as our SPT, which is widely used in the United States, was being developed. So they were pretty much side by side or hand in hand. And we first started using the Texas cone penetrometer in 1949. We published the correlation charts in 1956. In 1972, we'll see why our charts were updated and our design was modified. And then in 82 and 2000, we updated our correlation charts again. And more recently, we've done additional work on the reliability of the method. For those that aren't familiar with our Texas cone penetrometer, this is what it looks like. On the left, you've got a cone that's attached to a drilling stem, lower down in the bottom of the hole. And in the picture on the right, you see the hammer, which is an automated hammer, which is recent, incidentally. 170-pound weight has dropped 24 inches. This is a picture of our drill crew that went away, I believe, in 2014. And on the left, you see is Craig Mason, and on the right is Todd McBride. Our correlation charts, they've undergone several different changes. These are what's used to correlate our Texas cone penetrometer to shear resistance or point bearing, depending upon the circumstance. These are what our design methodology is based on, and this is the most recent curves. As I stated, our design methodology has undergone some changes, in addition to the changes in our charts. Back in the day, from 49 through 71 and earlier, spread footings were designed solely on bearing, piling on skin friction, and when drill shafts were introduced in the 40s, they were designed based on point bearing. Based on our research that was done through the University of Texas, we modified our design procedure, especially for drill shafts, because that's when we allowed for the combination or the use of skin friction. This changed everything dramatically because now we didn't need to bell our shafts anymore, and I'll discuss that in a minute. And that saved us and gained great economy. Spread footings went away because drill shafts became very popular and economical, and now they're only occasionally used basically in just rock. As I indicated, our bell-shaped footings went away on the left and were replaced with what's shown on the right, where the inclusion of skin friction was used, as well as end bearing. And so effectively now we could actually shorten our shafts compared to what was before. We didn't always have to get down into the most competent layer. So we've talked about the past, what's sort of some of the recent advancements that have gone on. In the time remaining, I'm going to look at briefly the following: large diameter mono shafts, these have come into play, and then foundation testing. Large mono shafts are becoming more and more popular. They're being used for a variety of reasons, a lot of which is constraints. As we tend to try to widen or advance our roadways, we're hemmed in, and so trying to place large footings, etc., are problematic, and so large diameter shafts are being used. This is a 12-foot diameter shaft, and as you see the rig on the top left, it's a very impressive rig, which could drill down. Slurry was used in the hole, and you get the magnitude of the size of it by the gentleman standing in the center part, and on the right is the lifting of the cage that's being placed. Well, there's advantages and disadvantages. As I was saying, TxDOT started using more of the mono shafts. With that comes a lack of redundancy. So if there are problems with the shafts, then they're much harder to fix and much more expensive. And so we've started looking at various testing methods, one of which is thermal integrity profiling. These are, on the upper right-hand side, what you see is a series of colored dots. Those are the thermal probes that are attached to the cage continuously all the way from top to bottom. They measure the temperature. Based on the temperature, then we can estimate properties of the shafts. Because there's a parabolic curve for the decay of temperature, with the highest point being in the center, the outside being the coolest. If you look at about depth 50 to 55 feet, you see the curves on the left-hand side bow to the right. That means they're hotter than normal. That means there's a bulge in the concrete. You see that in the three-dimensional rendition in the middle. At the lower part, you see two of the curves actually project to the left, That means they're cooler than what is expected, and therefore there's a neck, and you see that in the bottom where the rebar is actually sticking through. This gives us a number of things, one of which is the actual behavior or what the shaft looks like, the cross sections, and it is continuous, and it gives us results that are fairly quick. Now it won't go down. Sorry. How do I get it to go down? Press there. Oh, there we go. Sorry. Having technical difficulties, I apologize. Once we have that information, the next phase would be to actual test. I'm going to talk briefly about two different tests. The first is a statnamic test. It's a dynamic test. Basically, what you see in the upper left in my hand are the actual charges that are put in. They're installed in the bottom, which is shown in the bottom right. Basically, that charge goes off, and it attempts to lift the weights, which are shown in blue on the left. Based on that, in the instrumentation of the actual drill shaft, we can get what the load is, which is the dynamic load. That then equates back to a static load, and we can actually look to see what that capacity of that drill shaft is. Another way to test, and this has multiple applications, but this is high strain dynamic testing. This is a bit different than the other one. The other one included a sort of a charge, which actually trying to lift the mass. This is based on pile driving, shown on the left. You actually drop the weight onto, on the right, you see the drill shaft. The impact then is recorded. The values are converted to force, and the force acting on the top gives us the actual load carrying capacity. And then this can also be used to actually monitor the driving of piles, where we can obtain both the integrity, the installation behavior, and also capacity. So with that then, what I've done is I've tried to present today an overview of what the foundations are, sort of a little bit of the design of them, and the fact that we've had sort of a long-standing and successful history with their use. We've also been on the leading edge of research with drill shafts and advanced the knowledge not only for TxDOT but for the rest of the U.S. And so in conclusion then, let's see what the future has for us, and let's see what it does for us in terms of foundations. With that, I'll conclude, and I'm not sure if there's going to be time for questions. Is there? Okay, I can entertain a question or two if somebody has it. Yes, sir?
In regard to the tip testing, how soon do you think you get that into the specifications for the, I guess, inspector the redundancy, if you don't have redundancy?
The question is for the thermal integrity profiling testing, how quickly will that be put into the specifications? It'll probably be written, it is written into special specifications as it stands now, and then whenever the new spec book is, if it proves itself out, then it'll be considered for inclusion then. Any other questions? Yes, sir?
For the tip testing to work, does it matter if it's constructed dry or with slurry displacement?
No, sir. No. No, so the question, I apologize. The question was for the thermal integrity profiling, does it matter whether the shaft was constructed in the dry, meaning there's no water or slurry in the hole, or is it affected by slurry? And the answer to that is no, because the temperature is actually on the outside. The slurry gets displaced out of the hole, or the water in the slurry gets displaced out of the hole. So it's actually the ambient temperature of the material that's outside the hole that's going to affect that gradient that goes across it, not what's actually in the hole. Anybody else real quick? Yes, sir?
I was wondering, once you identify defects like you have shown, what remedial action is available to correct?
Okay. The question is, once a defect like the one that was shown has been observed, what are the remediation measures? And that's a somewhat difficult question to answer, but as all things in geotech, it depends. And the reason it depends is because we have to look at what effect it has, all right? And that effect is both in terms of its structural capacity and its long-term behavior effects. In terms of structural, if it doesn't affect it that greatly and we're down deep enough where it's not going to create a corrosion problem, if it's relatively minor, that may be let go. If it's a true defect where it's going to affect structural capacity and its behavior, there are different options, all right? They can actually core the center of it and then use high pressure washing to try to get the concrete out to reestablish the section. They can supplement with a different drill shaft. There's a number of things that can be done, but it's really the function first of how bad is it and where's it located.